So this is inspired by number 23.
23-ish.
Right, 23-ish in 14.1. Okay, so they want me to come up with where is what?
Waldo.
X
GX.
equal to 0, and B, which we shall do in green. Where is GY 0? And presumably this picture they gave me is of G, right?
Mm-hmm.
And there's some labels on these level curves, but that actually doesn't matter at all. Okay?
Mm-hmm.
So, what does it mean for the x derivative to be 0? It means the tangent line in the x is horizontal, right? What's that going to mean?
There's no change in the z at that point.
Yeah, there's no change in the z in that direction, right? So if I was standing at one of those spots, like if I had x this way and y that way and z was height, that means when I look out along the x direction, right, there's no change in height.
Mm-hmm.
What's that mean?
Are we assuming that that's y and that's x?
Yeah.
Okay.
Or this maybe that could be at the top of the hills, right? Because
Okay, so yeah, definitely the top of the hills, right?
This saddle as well.
We
Where
see
it
that.
curves have
So,
horizontal tangent.
so definitely these guys, right?
and the curves have a horizontal tangent.
Yeah, in any place that like this is happening. You see that?
Right. So
Any place I'm standing on a level curve that's parallel to the x, right?
Mhm.
Okay, so
this is a top
yeah, there's a ton of them, right?
And then the saddle point should also be.
And probably the saddle, right? I'm assuming it's in the middle there. That's really just a wild assumption, right?
Right.
If I kind of thought about filling in more tangent lines or more level curves, right? Like they gave me levels at 10, right? If I filled in more of these, right, presumably the next one looks like this, which means there should be a point here. Okay, see that? So I'm going to get a whole little set of points. What's it going to look like?
Just the tops and bottoms of the blobs.
Yeah, okay.
You could
so
draw-
like here and
Yeah,
here.
you could draw a line running through both points.
Yeah, it's gonna be some kind of funky curve, right? You guys all see that? Maybe like. Oops, I didn't do a great job. I missed that last one.
Yeah.
Okay, see that?
Alright.
It's gonna be something like that. How about the other ones?
It's gonna be vertical tangent.
Okay, I'm looking for, yeah, any spot I'm on a level curve vertical, right? So like these guys. Again, the tops, right? And then, oh, on the other sides, right?
Yeah.
Saddle as well.
Okay.
There's a few extra points there as well. If you go back a little.
There's a few extra points.
Yeah, in the center.
Oh yeah, so of course I've also missed the fact that I should really be connecting these dots, right? Okay, so I might connect the dots. Let's see, where else?
On the ends.
On the right.
Yeah, these
Oh.
guys.
And then on the right as well.
Over here.
So when you cover a mound, it would start looking like a net. With these Ys
Yeah.
and Zs.
Yeah.
X's.
You guys see this?
Yeah.
So there's kind of a whole bunch of these. The ones I know for sure, right? The ones I can actually pin down are these ones where the level curve's pretty clearly tangent to the axis or
So,
parallel to the axis.
so this would be like gradient descent if you're finding minimums in.
Oh yeah, this is a method that yeah, people use to find minimums. Yeah, you walk out along the gradients, which we need to talk about today because gradients are a nice optimum way to do that.
Right.
This is This is not quite gradient descent because here I'm not. Well, no, it is gradient.
Because you're mapping to the lowest and highest points in each case.
Yeah, but the way I'm doing it here is I'm connecting the spots where one of the partials is 0, right?
Uh-huh.
And that kind of wander is going to be
Different because you're not
Similar,
always
but
looking for the average lowest slope. Is that why?
so gradient descent's gonna tend to be perpendicular to this, but maybe not exactly perpendicular to this.
Okay.
Yeah, totally true. Yeah, I think that'll be. Let me not say too much on that.
Okay.
Gradient descent's a super useful tool, and it's at least a little bit related to the idea.
Okay.
Anyhow, let's see. I've got. Oh yeah, all sorts of connecting bits and pieces here, right? Okay. Well, let me not spend a bunch of time drawing the connecting bits, but we could, right? We'd need like this one here, and this one over here, and this one up in here, and this one right. I don't know where the heck that one went. That should go. I don't know where the hell that one goes. Where does that one go? There should be a spot off the other side there.
Not as it's drawn.
No, not as it's drawn. Huh. I didn't know where that one went. That's why it's not gradient descent.
Why?
Because I didn't know where that went.
Oh.
On gradient descent, you would fall off both sides for sure.
Mm-hmm.
And on this, I'm not.
Because with gradients,
I'm hoping it's just bad picturing.
Because in that case, you're using the actual slope of G rather than its components. Is that the difference?
I'm only using one of the components of its slope, right?
Right.
This function G has 2 directional derivatives, right? And when I'm drawing either the green line or the blue line, I'm only using one of those things.
But in gradient descent, you'd be
You
using
use
both.
yeah.
Okay.
Yeah, it's a little bit stronger, right? It's a better tool because it includes all of
Right.
that slope
Okay.
information.